To start Chapter 6, we're going to combine the first two sections, 6.2 and 6.3, to take a really in-depth look at a normal distribution. But first, let's look at distributions in general, specifically density curves. A density curve is used for continuous probability distributions. So this is for variables that are measured versus countable, and it must satisfy the following two requirements. The total area under the curve is equal to 1, and each point on the curve has a height that's 0 or greater. The first one we're going to look at is a uniform distribution. In a uniform distribution, all the values in the distribution are spread uniformly or evenly over the range of possibilities. The graph of this is just going to be a rectangle, as shown here. So in example 1, it says the Newport Power and Light Company provides electricity with voltage levels that are uniformly distributed between 123 and 125 volts. Now, when we look at this, it didn't tell us that the height was 0.5. However, we can figure that out by looking at the bottom here and seeing that this spans 2 units, and we know that the full distribution has to equal 1. Area is base times height. We know that the area is 1. We know that the base of it is 2, which means the height needs to be 1/2 or 0.5. So for part A, find the probability that a randomly selected voltage is A greater than 124.5 volts. So we're going to draw a line here, 124.5. We want to find the probability of ending up in this section of the rectangle. And this just ends up as a geometry problem. So we have a rectangle here. The base is 0.5, and the height is 0.5. So 0.5 times 0.5, 0.25 is our answer. Okay, less than 123.3 volts. So we're over here this time in this section. Okay, the base for this is 0.3, height of 0.5. Base times height again gives us a probability of 0.15, 15%. We'll see uniform distributions from time to time, but most often we're going to be working with the normal distribution. This is that bell-shaped curve that we've been talking about since the beginning of the course. It's a density curve because the total area underneath the bell curve is equal to 1, and all the points on this bell curve have a height of greater than 0. Okay, it's never actually going to reach the x-axis here. It just gets closer and closer and closer to it as we move away from the center. Back in chapter 4, we did z-scores with this equation, x minus the mean over the standard deviation. So now let's use the density curve for the standard normal distribution to find some probabilities. So let's say a data value has a z-score of negative 2.12. Okay, so to start, we would write this like this. We want to find the probability that a data value in that curve has a z-score less than negative 2.12. Here's our standard normal distribution. We want to end up in the part of the curve that's to the left of negative 2.12. All right, now I've given you a standard normal distribution table with all the probabilities. It's a big table of numbers. This looks like the top part of one page. Okay, if you look at the side of it, there's one side that has negative values, the other side has positive values. We want to be on the negative side because we're going to look for this number, negative 2.12. All right, so when we look at this table, the first thing we see on the left side, it says z. Okay, so we want to go to the first two numbers in our z-score, negative 2.1. Okay, we're cutting off the 2 for now. So 2.1 is on this line right here. Okay, now we want negative 2.12. So we find the intersection of that 0.02, which is going to put us on that value. Okay, negative 2.1, 2, 0.0170. So the probability that a value has a z-score less than negative 2.12 is 0.0170, or 1.7%. Example 2b, find the probability that a data value has a z-score greater than negative 1.96. So we would write it like this. The probability, P, that it's greater than negative 1.96. Okay, so we are about here. We want everything to the right of that. All right, now this is going to have an extra step because anytime we look at this table, it's always telling us what's the area to the left of that z-score. So we're going to look up negative 1.96. We're in the bottom row of this table here. Okay, we're going to go over to where it intersects with that 0.06. So negative 1.06, negative 1.96 is 0.0250. But what that's telling us is that the area to the left of this is 0.0250. Okay, so this section over here is 0.0250. Okay, but we want the red section that's to the right of that. So what we have to do, since this curve totals 100%, we're going to do 1 minus what the table gives us. All the elements in this table are the values to the left, the area to the left of that z-score. Okay, that'll give us the area to the right once we subtract it, and we get 97.5% of our values are to the right of that z-score. In this problem, we have two z-scores. Find the probability that a data value has a z-score in between 0.25 and 1.25. So we are looking for 0.25, so let's say about here, 1.25 about here, this section in between the two. Right, we would write it like this. Z is in between 0.25 and 1.25, or 0.25 is less than Z is less than 1.25. All right, so to start, 0.25 on this line over to 0.5, negative, or I'm sorry, 0.5987. We'll never get any negative probabilities. Probabilities have to be between 0 and 1. All right, so when we look at this value for this line to the left of this line is 0.5987. Okay, now we want to look up 1.25. All right, so we're at 1.2 on the bottom here, over to the 0.05, 0.8944. Okay, for this line here, if I extend it up and go over, we get 0.8944. So if we want to find out this section in the middle, okay, we're going to take this blue value and subtract the whole green value. Okay, that's to the left of that. Okay, that'll leave us with that red cutout value. So we subtract them, we get our answer, 0.2957. One more just to make sure we're clear on this table. Find the probability that we get a z-score greater than 1. Okay, we're looking for to the right of 1.00. Our z-scores are always to 2 decimal places. 1.00 on the table is 0.8413. But again, this is always giving us the area to the left. So that tells us that this part is 0.8413, which makes sense. Okay, because the middle of the curve at 0, 50% is to the right, 50% is to the left. So based on that, we should know this should be less than 50%. Okay, 0.8413 wouldn't make sense. We want to subtract it from 1 to get our answer, 0.1587. So what's the point of all this? This bell-shaped curve, the normal distribution, occurs naturally all around us all the time. So when we're told that we have a normal distribution with a certain mean and a certain standard deviation, we can find the probability of any event in that distribution. For example, American households generate an average of 28 pounds of newspaper recycling. Okay, we're assuming this is normally distributed. It most likely is if we were to look at the data. We have some average value. Some people generate more than average. Some people generate less. As we move away from that average, it becomes less and less likely. It tells us the standard deviation is 2 pounds. Okay, and then it asks us what's the probability that a household generates more than 30.2 pounds per month. So we have this distribution here. We know that the average is 28. That's going to go right in the middle. Okay, and the actual distribution we would write like this. N parentheses 28, this is the mean. 2, which is our standard deviation. We're trying to find what's the probability that we end up with 30.2 or more if we randomly select a household and find out how much newspaper they recycle. So first thing we want to do is we want to standardize this curve, which means we want to find a z-score for this. We always take our x value and we subtract the mean. 30.2 minus 28, divide that by the standard deviation, and that gives us our z-score 1.10. Now it's just like the previous problems we did. So we load up that table, we find 1.10 in this table here, 0.8643. Remember, this is telling us the area to the left of this line. So this is 0.8643. To find the probability that a household generates more than that, we would do 1 minus. Okay, and we get 0.1357. If we looked at IQ scores, we would see that they follow a normal model. They have an average of 100 and a standard deviation of around 16. What percent of people should have IQ scores above 120? Here's our distribution, 100 right in the middle, standard deviation of 16. We can always pull those parameters right out of this little n parentheses thing. Okay, we want to find the probability that we end up at 120 or more. So 120 to the right. Anytime we do a z-score problem, we want to draw this curve, have this written, okay, along with the shading. Find the z-score, 120 minus 100 over 16. We get 1.25. Jump to the table, look it up. 1.25, 0.8944. And again, we want to do 1 minus that to get our answer. 10.56% of people have IQ scores above a 120. Let's do one more just to make sure we're clear on it. We have IQ scores again, centered at 100, standard deviation of 16. It's saying what's the probability that someone has an IQ score between 65 and 90? 65 to 90. Okay, and we want to find the probability or the area in between those two cutoffs. So we want two z-scores for this problem. We need a z-score for 65. I'm going to call this one ZL for the lower z-score. And then we need another z-score for the higher one, the 90. Okay, we calculate them both the same way. We get negative 1.75 for the lower one and negative 0.63 for the higher one. We always round z-scores to the closest second decimal place. We go to the table, we look these up, and we get these two values. So for the higher one, we get a value of 0.2643. And for the lower one down here, we get 0.0401. So to find the area that's in between those two values, we're just going to take the bigger one, subtract the smaller one, and we get 22.42% of people between those two IQs.